So hello, everybody. My name is Jacopo Pantaleoni. I feel it might be a little difficult to entertain you for a couple of reasons. One is that the speakers before me were really excellent, so it might be difficult to get on par with them. The second is that I'm probably the only one in this room who has never done really any VR. But they asked me to talk a bit about but I will talk a bit about real-time rendering and the latest advances in real-time rendering. And they asked me to talk a bit about my past. Probably because that is still more entertaining than anything I've done afterwards. So here we are. And that's something, if it starts, that I have been doing in the past. I've had the pleasure to work on a great movie that you might have seen, which was almost entirely rendered. And so it might fit still with what I'm going to talk about, although it's not going to be about movies. And luckily, that was the last movie I've been doing. But I've been doing other stuff which is also very interesting, at least from my point of view. And that's the argument of this talk. So the thing I'm going to talk about is that last year, well, first of all, I work for NVIDIA, which is a company building these guys, these microprocessors on your left. And they are graphics microprocessor, used to do mostly real-time graphics for games and whatnot, and for VR, of course. But they are used also for movies, and that was my contribution to Avatar. I've made the rendering for that movie, the rendering framework for that movie, which was running on a bunch of these processors, quite a few. But the point of this talk is that last year, we announced, actually, this guy over there, Jensen, the CEO of NVIDIA, announced a new processor which can do real-time ray tracing. And you might ask me, what the hell is that? But I'm going to tell you what it is, and I'm going to tell you why it is probably the most important change in the foreseeable future of graphics. Although I know you guys are all interested in VR first and foremost. But ray tracing is probably an opener to a lot of technology that will allow better virtual graphics, so virtual reality graphics. So whatever, and I'm going to talk about virtual in the sense of stuff that doesn't exist, that you want to visualize, and so not necessarily related to virtual reality in the sense of filming something and showing it on a virtual reality display. And this technology, RTX, that's what we announced last year, is a bit of ray tracing hardware. It's the first bit of ray tracing hardware available publicly, basically, which we developed in the last 10 years, more or less. But what is it? So ray tracing is a family of algorithms that allows to render photorealistic pictures of things that do not exist. And it's not new. It's been there since, I think, the late 70s. It's definitely not new. But what's new is that we have made it in hardware. Before it was used in software, we've made some silicon that runs ray tracing algorithms. And what is it? Well, when you see anything, or when your camera sees anything, or your camera, well, our eye as well, has a bunch of sensors, but the camera has simpler sensors arranged in a grid of pixels, like the ones you see on your screens. When you see anything, it's actually photons, which more or less travel along straight lines, that coming from a light source touch some object and bounce around, and bouncing around finally arrive at your sensor. So at some pixel on your sensor, and leaves a mark there. And in practice, reality is slightly more complicated than that. because on that line coming through that specific pixel, a lot of photons come through. And they all bounce around many times before actually hitting that sensor. The point is that they actually billions of rays bounce around on the same point on the floor, and then they get to your eye or to your camera sensor. And what we do in graphics to create beautiful pictures like the ones you have seen in Avatar is doing the reverse process. We cannot shoot a gazillion photons like reality does, because that would be too expensive, but we simulate the reverse of a photon starting from the camera and trace rays into the virtual scene until it touches some object and then starts scattering around, so that we can actually simulate the process that nature does in reverse until we find, hopefully, a light source. And the average of those contributions is the color of the pixel that you see. And why is it complex? It's complex because each ray has to be intersected against some scene representation. And the scene representation is typically made of meshes, triangle meshes, often containing millions of triangles. This is a super simple model nowadays, by nowadays standards, and it has 871,000 triangles. So each ray has to be tested against all this triangle mess. And of course, this algorithm can be improved. Instead of testing each ray against each triangle there, we can basically build a spatial database to speed up the search for the important triangles that might be hit by that ray, and so on. But it's still a very complex process, a very complex algorithm, even for just a single ray. And that was the simple model, but this is actually one model from this movie that you've seen before, from Avatar. And you can see that on the upper left, you have the whole model of this terrain with those rocky arches. But then you can zoom in, and you see more geometry, and you can zoom in on that square, you can see more geometry, and then you can zoom in on that square, and you can see even more geometry. And that's why rendering Avatar was challenging, because each shot contained billions of triangles, not millions. And that's why we needed to create a new rendering framework for that. And why is it complex again? Why is it considered still a complex process? Because if you take a 1080p video running at 60 hertz, which is not even that much compared to what gamers expect today. Many gamers expect running at 120 FPS or even 200 FPS. But even at 60 hertz, 60 FPS, you have to push 124 million pixels per second. So if you have some rendered content that you want to render in real time, that means you have to render at least 124 million pixels per second. And in practice, you might need to cast at least one ray for each pixel. In practice, it's a lot more, but I'll talk about this in a second. But these are some numbers. So at the time of Avatar in 2008, when we made Avatar, we could ray trace on fancy processors, very fancy processors, not the kind you would find at home, but still processors that we build, between 15 to 100 million rays per second. So on these very bulky, very speedy, beefy processors that we built back then. And that was already state-of-the-art, by far faster than anything anybody else could do in the world. So today, after this announcement that we made last year of this ray tracing hardware, this custom hardware that we built exactly for executing this process, we can ray trace between 1.5 and 10 billion rays per second. So it's roughly a 100-fold increase in performance in 10 years. And mostly, actually, this 100-fold increase materialized last year because we were actually able to build this custom hardware. So without it, it would be much less. It would be maybe a 10-fold increase in performance due to the 10 years that passed by to the common technological advances. But it's much more. So why do we need it? Why do we need ray tracing for creating beautiful pictures? Well, it turns out that if you don't simulate, I mean, something I forgot to say. Like, before ray tracing, you could still do real-time graphics. Everybody does it. Every video game does it. Except that they are cheating a lot. But the interesting bit is that without ray tracing, the other process, which is typically used to display pictures of stuff that doesn't exist, is called rasterization, which is only a technique to show what's directly visible in front of you, but doesn't allow you to simulate light scattering, producing all these nice and subtle effects of illumination. So it only allows to simulate what's called a direct illumination. That doesn't exist in real life, because in real life, light does scatter. But it means basically that it does allow only to visualize the light that comes directly to your light sources, and it's directly the surface you're seeing, and then it's your eye, without any bouncing. So just one bounce. But in many scenes, if you only did direct lighting, so if you only rasterized your scene and used the common tricks to do shadows and stuff used in games until last year, on some scenes, you could only see this. That's the direct lighting in some closed space. So there's some light coming from the sun, and it's the floor, and you can see nothing else. But actually, this picture, if it was simulated correctly, would be this. And this comes after an enormous amount of rays are shot into the scene after one of these nice simulations. So billions and billions of rays. Because each point that you're seeing on this screen has to compute some very complex simulation of what light actually does. And with this process, you can create any photorealistic scene you can imagine and bend the laws of reality a bit. And it's really convenient to do anything from visualization to architecture, because with this kind of realistic simulation, you can freely change the materials, freely change the mood of a picture just by tweaking light sources, or again, tweaking materials and make something made of glass. So the mood of the picture is instantly changed with a few touches. As opposed to a lot of artists' time being put in faking effects, as the game artists typically do. Like in a typical game, that's an interesting fact. A typical game production of a AAA game today is more complex than a movie production. And that's why I'm not working on a sequel of Avatar anymore. And why is it more complex? Because they're still using these faking techniques most of the time, which do not involve ray tracing, although they're starting now after our announcement last year, which require a lot of artist time being put in simulating nice pictures without running actually the proper simulation in real time. So we introduced this marvelous piece of hardware, but as a caveat, these simulations are still very complex. So even to render a single frame, you don't need one ray per pixel. You would need hundreds or thousands or often hundreds of thousands of rays per pixel to simulate what photons actually do. So even with very quick hardware, you can have this kind of response time on that scene before, actually a bit faster now. This video is from last year. But it still takes some time to have a converged picture. So to have a picture which actually looks not noisy and nice and smooth and resembling of what reality would look like. So despite this marvelous leap in performance, this is not enough. So we started some parallel effort back in 2012, and this was from some Finnish colleagues of mine, also working for NVIDIA research, that tried to bootstrap what's so-called denoising, research on denoising. So denoising means basically trying to find more information in a noisy picture than what you actually see. So taking a noisy picture as input, in this case, for example, highlighting depth of field, so simulating depth of field from a camera lens, and trying to find all the information in this picture to actually recreate a non-noisy picture without running a very expensive simulation. And that's what they achieved. So from exactly this one sample per pixel amount of information, they could extract a nice and beautiful, smooth picture. And nobody back then believed it was even possible, so it was really research. So this looks really realistic. If you didn't denoise it, it would have taken quite an amount of rays to produce such a picture. But that was the result back in 2012. And then we started applying this kind of techniques to every custom, every typical gaming effect. There's another gaming effect used to simulate, to fake, in a way, this light transport, these more complex light transport simulations. And it's called the ambient occlusion. But without going into the details, this is one pass, one rendering pass in a typical game. And with one sample per pixel, you can get this, which is still too noisy to be displayed, to be used. And with some denoising, you can get this. And this is some recent result we presented last year. And the same for shadows. Not so nice. Even if you can do this in real time now, it's amazing that you can do it in real time now, but it's not enough. But luckily, there's more information than your eyes sees. And the same for reflections. So for reflections, simulations are quite costly and quite complicated. So you can get a star field of noise, but luckily, again, even in that noise, there's more information than you would believe, and we can reconstruct this picture without tracing any more rays, just by blurring stuff accurately. So that's a bit what we have been doing, and this is a video that I showed last year when we announced this new hardware, showing a bit of everything, like what you can do now in real time with this custom processing. Maybe if we could lower the audio a bit, would be great. So that's real-time shadows. I guess there's no way to go on a fast forward of the video. It would be nice if we could show you, but jump on a more interesting point of the video. Maybe I can. anyway, you can believe me, we can do this kind of rendering now in real time, showing very nice lighting, which is a first, because it's actually simulated and not cheated. And this kind of algorithms is now being adopted in all major gaming titles, like Battlefield, Shadow of the Tomb Raider, Metro Exodus, and some more. And this, for example, is an example from Metro Exodus. Some picture without ray tracing, showing only direct lighting, plus a bunch of artistic cheats to simulate a bit what global illumination would look like, so what real lighting would look like. Quite a bit of cheating. And with the new kind of simulations, you can add a lot more realistic feel to it. And it's interesting that this picture, which is still not as nice as this one, but this involved already a lot of artist time just to put light where there would be none without a proper simulation. So this was Metro Exodus. These are some examples from Control, which is probably my favorite. This is without ray tracing, what you would find in the game, in the game without this ray tracing hardware that we introduced, and this is the result after doing the proper simulations. And again, some more picture. You can see there's more reflections and everything. But the most interesting bit is, before going further, this is a demo that we have made together with ILM, Industrial Light and Magic, which is the company, the studio that, to give you some idea, made the Star Wars movies and a lot of other movies. And we collaborated to show the potential for this kind of real-time graphics. And this is a video that runs in real time. It's not actually a video. It is a video here, because I recorded it, and I'm going to show you the video on this laptop. But actually, it's something that you can run in real time, so you can interact with, actually. Let's see if it works.
What's the story with all the elevators lately? I heard Kylo Ren destroyed the one over in D sector.
If you ask me, who's ever in charge of this place should be transferred to Hoth. What? What?
You think she heard us? Yeah, I think she heard us.
At least we blend in for once.
So this hopefully gives an idea of what kind of effects you can now achieve in interactive content. So you can, especially for people who develop VR applications or augmented reality applications, this, I guess, could be interested to open doors to special effects there, which look like reality and not just something juxtaposed badly to reality. And to finish, there's another video showing actually a piece of this new game, Control, which uses ray tracing. And it shows the before and after. And this is a game. This is actually footage from somebody playing the game. So there's quite a leap in quality. And it's funny, because all of my life I've not been too attracted by games, by the games industry, because the images were crap compared to the movies. And to some extent, it's still true, but it's getting there. It's really getting there. There's too much violence for my tastes, but still. The quality, at least, of the graphics is getting much more pleasant to the eye. And that should be it. And feel free to ask questions. Thank you so much.